All right, and the final set of equations that you're going to work with here, we're going to talk about escaping Earth's gravity well, or any planet's gravity well for that matter, and energy for an orbiting satellite. So let's talk about escape velocity. All right, so escape velocity. In order to escape Earth's, if you want to figure out how fast or what velocity we're dealing with here for escape velocity, EK will need to be EG. So that's 1/2 mv squared is going to have to equal the gm m over r. So we're using the from the previous formulas, the energy to escape Earth. And so move the satellite beyond the reach of the Earth. When we do that, we find that the mass of the object actually cancels out. Multiply both sides by 2 to get rid of the 1/2. I still have v squared. So 2gm over r, or square root of 2gm over r, and that'll be in your meters per second. So that formula gets added. Okay. And that is your average velocity on the trip. All right, so keep that in mind. So this is average velocity on trip to escape the gravitational field. So escape velocity, but it's not a calculation on how fast you got to go, and that's how fast on average you need to go in order to escape. The second, or I guess the last formula I'm really interested in, is we know from grade 11 again that your total energy when you're climbing or going up, so if you're in a rocket, is going to be EK plus EG. So kinetic energy, we're going to look at it as being a positive value, all right, plus we take that escape energy, gm over r, and it's negative because how we view it as stored energy. All right, stored energy. So that's how much energy an object has or is being stored with as it travels up. So before I go any further with that one, I'm going to just do an interlude here. So if I go back and talk about force for a second. So from force, what do we know from our force? So if we look at centripetal force, mv squared over r, if we set it equal to force due to gravity, gm m over r squared, we talked about this in a previous slide, r would reduce, and we have mv squared on the one side, equal to, so mv squared equals gm m over r. So what I'm going to do is I'm going to do a substitution. I'm going to take this value here, the mv squared, and I'm going to substitute it into that term right there so that we can finish that equation. So underneath here, I'm going to have 1/2. That substitution is gm m over r. And we get rid of the double signs, minus gm m over r. Like terms, so I have a half minus the other. So total energy is equal to negative 1/2 gm m over r, or negative gm m over 2r. So there is your total energy, and that is the energy of an orbiting satellite. And that's because I set, because I want the total energy here to make sure we have enough energy to reach orbit. So we set it equal to each other. So we end up with the energy of an orbiting satellite. So you can see how important it is not only putting some of these formulas on your study sheet, but also making sure that they're clearly labeled for future use, so you know exactly what you are calculating. So those are finally the last two formulas, and I do apologize for the length here, but it's just so much of it's interlinked with each other, and a lot of the questions are just going to simply be a question with A through E. It just seems silly to break it down into components when I'll just give you all the information and you kind of work through the problem all at once. So let's see an example worked out here. So we have a 500 kilogram rocket. They want to put it in a circular geosynchronous orbit around the Earth. The period, so I'm going to start writing down some information here. So first of all, we know M2 was 500 kilograms. We're going to put it into orbit. We know the period is going to be 24 hours. Now remember, we want that in seconds, so we'd have to multiply it by 60 because we do work with the physics in SI. The mass of the Earth, it's given information, so it's really mass of the source here, so capital M equals 5.98 times 10 to the 24th kilogram. That's all the information that's given. So we want to answer the following. One of the other pieces of information I might as well grab right now, radius of Earth, 6.38, and that's going to come off again. You're going to have a sheet with all these values or constants listed, so you're not memorizing anything. So what is the radius of the rocket's orbit? So we need to figure out R. R is the unknown. What do we know? It goes into a synchronous orbit, and we know period. So does the formula with period, help us determine the value of R? And the answer in this case is yes. So from the formula from the previous slides, we get 4 pi squared m R equals gm m, and I think that's R cubed, my mistake, and we still need that period up there, t squared. One of the things I think when I did that previous formula, the m's will cancel out, our mass of the objects actually cancel out here. So we are looking for R. So I'm going to, before I put all the big numbers in, I'm just going to isolate for R cubed. So I'm going to divide both sides by 4 pi squared. And what I'm looking for is the cube root of gm t squared over 5 pi squared. So that'll give me the radius of this particular rocket's orbit. And you'll notice the mass of the rocket plays no role. So 6.67 times 10 to the negative 11, 5.98 times 10 to the 24, multiplied by 86,400 squared, divided by 4 times pi squared. That's all inside the square root sign. And when you go through and do those calculations, you should get 4.2 times 10 to the 7th meters. So 4.2 times 10 to the 7th meters. So therefore, radius of orbit is 4.2 times 10 to the 7th meters. So there we go. A part done. B, what is the GPE of the rocket when it's sitting on the ground before launch? So we are looking at gravitational potential energy when it's sitting on the ground. So how much energy would it take to move this rocket beyond the Earth's reach? So gm m over r. So the amount of energy, how much energy is it stored just sitting on the surface? Well, we're looking at the total amount of energy it would take to move it beyond the Earth's gravitational field. So 6.67 times 10 negative 11, 5.98 times 10 to the 24th. Mass of the rocket, I think it's 500, divided by the radius of the Earth, because it's sitting on the Earth's surface right now. So 10 to the 6th. And when you calculate that, you get 3.1 times 10 to the 10th joules. So therefore, the rocket has 3.1 times 10 to the 10th joules of energy on the Earth's surface. All right. C part, way up here. What's the total energy of the rocket when it's in orbit? So again, you're just looking at the formulas that are provided there, and the formula for energy of a rocket in orbit is, oops, sorry, right there in that slide at the bottom, right here, ET. All right, so returning back, our total energy, negative GM M over 2R, negative 6.67 times 10 to the negative 11, mass of the Earth, 5.98 times 10 to the 24th, 500 kilogram rocket, and we're going to divide that by, in this case, by the radius of the Earth, 6.38 times 10 to the 6th. In this case, it's going to be a negative value because it's what we call stored energy, 1.6 times 10 to the 10th joules. So therefore, orbiting satellite has negative 1.6 times 10 to the 10th joules of energy. D part. So D part. How much work must be done to put the rocket in orbit? So it's basically we're moving rocket from R1 to R2. So that means we are looking for EG equals GM M 1 over R1 minus 1 over R2. So substituting in their values, substituting in all our values, we have G times capital M times M, and then R1 is the radius of the Earth, R2 is the orbital distance. Calculating that, we get 2.7 times 10 to the 10 joules. So therefore, to put it in orbit, you need 2.7 times 10 to the 10th joules. And E part, how much additional energy would the satellite require to escape from Earth's gravity well? Well, if it takes 2.7 times 10 joules to get it into orbit, therefore, energy required is anything greater than 2.7 times 10 to the 10th joules. So if you went 2.71, you would then get out of orbit. So it is kind of that finicky in order to break that orbit. So again, I apologize for the length, but like I said, in this case, it's one of those things where all the questions are garbled together. So you need all those formulas, you need all the theory up front. So normally it would have been 2-day lesson, 2 to 3 days of work. So you know that this, now you don't need to watch videos for a couple of nights as you work through the handout that's provided in class. If you have any questions or you want anything clarified, please make sure you mark which parts need further evaluation or explanation, and I'll attempt to clear them up in class. And can't spell homework apparently. Put an E in there. All right. Good luck, and we'll see you tomorrow.